Brake pads are the interface between the caliper clamping force and the spinning brake disc. The friction force and therefore brake force is directly proportional to the coefficient of friction at that interface, which is mostly a result of the pad compound. However, the pad compound dictates a lot more than just the magnitude of the friction force, and there's a huge range of different compound options available. There's also a lot more to pads than just the compound of the friction material, but it is the key consideration when choosing pads for a vehicle, so it'll be the primary focus of this module. The different choices of compound can make or break our braking performance, so it's important that we get it right for our vehicle, setup, and required characteristics. Remember, during braking event, the key process is converting kinetic energy into thermal energy. The retention of that thermal energy in the pad depends on the conductivity of the compound, and different compounds have different operating temperature ranges. If the pad can't dissipate enough heat quickly enough, they'll soon overheat, seriously compromising the braking performance. As we discussed in the brake system components section of the course, to a large degree, the brake disc we're using will dictate which style of pad we use. However, for this module, we'll be focusing on pads to be used with iron discs, as these are by far the most common in street and motorsport applications. In the components section, we also discussed the different materials and manufacturing processes that are used for pad compounds and their trade-offs on performance and comfort. So if you're a bit hazy on the subject and need a refresher, I'd recommend revisiting this section before carrying on. The best method of determining the right pads for you is to talk to the supplier. But before we can do that, we need to have a clear understanding of the application so that we can provide them with enough information to base their judgment on. The application being what kind of car they're being used on and what that car will be used for. This will paint a picture of the performance and comfort requirements. For example, a street car needs pads that will work well from cold and produce low noise and brake dust, whereas an endurance car that sees formation laps and rolling starts has the opportunity to warm the brakes up, so the cold performance is irrelevant, as are the comfort aspects. What they do need to do is to be able to withstand very high temperatures. Let's take a look at a typical plot that we'll often see used to explain the differences in characteristics between various pad compounds. Each line on the plot is a different pad compound. On the vertical axis we have mu, which as we know is the coefficient of friction, which all other things being equal, basically equates to the braking force. And on the horizontal axis we have the operating temperature. What the operating temperature actually represents can vary on these plots between different manufacturers. Sometimes this represents the pad temperature, but more often than not it will be the disc temperature, simply because it's more practical to measure. Regardless, the heat of the two will be comparable and follow the same trends. The plot for each compound shows that below a certain temperature, mu is essentially zero, meaning it won't produce any friction force. Then, as the temperature increases, the friction picks up and stays roughly constant throughout the temperature range, which is in our operating window where we want to be working. If the temperature continues to increase, the friction will drop off again as the pad overheats. The rate at which the friction picks up and drops off, the average mu value across the operating temperature, and how consistent this is, as well as the actual range of the operating temperature, all varies from compound to compound. We can see here that compounds with higher mu values at lower temperatures tend to have a lower maximum mu value compared to other compounds, meaning compounds that work well from low temperatures are generally those that provide the least braking force. For those capable of the highest mu values, the operating range tends to be at higher temperatures, and this means that the highest friction pads require more heat to produce this friction. It should hopefully be obvious by now that generally speaking for street cars, we'll be using compounds with lower operating temperatures, and this usually means they produce lower levels of friction. As the form of motorsport competition we're competing in gets longer and more intense, the operating temperatures rise and the pads produce more friction, which does come at the compromise to disc life, noise, dust, and expense. We can use data from temperature sensors or other methods like brake temperature paint to determine the operating temperature of our brake system, and this can also be tuned by modifying the brake ducting. We'll be coming back to cover tuning brake temperatures in an upcoming module, so don't worry too much about this aspect for now. The kind of plot we just looked at is what we'll commonly see used by manufacturers to explain the operating temperature and nominal coefficient of friction values for their different compounds. It's a helpful tool for letting us make the best decision for our application, but it doesn't tell the full story, and sometimes we need more information. When manufacturers are developing pads, they usually test them on a brake dynamometer, plotting braking force versus time for a series of successive stops. The same data can also be collected on a track, but it's obviously in a less controlled environment. It's unlikely that we'll be able to get access to these results from the manufacturer, but it's still worth understanding the important aspects seen in this example from AP Racing. Since the brakes are starting from cold, we can see that the first few stops show the cold performance of the pad. Once the brakes have heated up to their operating temperature range, it's possible to see how much friction they can generate, but also how the friction varies throughout the stop, as this has a dramatic effect on the feel of the brakes and how easy they are to use. Ideally, what we want is a strong initial bite with the friction slightly and gradually decreasing and then stabilizing through the stop. What we don't want is the initial bite to be low and then the friction to rise throughout the stop, as this is usually the hardest for the driver to control and modulate. This does depend on the aerodynamic downforce of the vehicle though, with vehicles producing higher aero loads being able to make use of pads with higher initial bite. As all other things being equal, they will have more grip at the maximum speed when the brakes are applied. Naturally, pads with higher initial bite will increase the chances of the brake locking, but this will be more of an issue for vehicles producing less aero downforce. As the stops continue and the brakes heat further, we can understand how the brakes fade with high temperatures. In an ideal situation, the brakes wouldn't fade, but there's always going to be some temperature range that we need to stay inside. Fade can be recognized by the pedal feel remaining firm, but the driver has to apply much more pedal force to slow the car at the same rate. Assuming the vehicle has already been tested, it's likely that the current pads have presented some issues or are just not ideal and shows some room for improvement. This means we can analyze the current problems and choose a more suitable pad. Again, we really need to use data from sensors or temperature paint to define the operating temperature of our braking system and determine if we're within the optimal range for our pads. If our brake temperature is too cold or too hot, then we need to reduce or increase the brake cooling from any ducting we may have, or change our pads to suit the temperature range. With that said, with what we've already learned in this module, it's relatively easy to tell if the brakes are too cold to be effective or too hot and begin to fade, even without the use of data. If we have issues with how the brakes feel, then this is a bit more subjective, and it's really best to talk to the supplier about their recommendations. At the end of the day, testing and experience is always going to give us the best information. If excessive noise, dust, or disc wear is an issue, it's likely the pad compound is too aggressive for the application, and some compromises to performance may be required to avoid these issues. However, it's worth looking into alternative pads from different manufacturers, as it's often possible to find different compounds that minimize these issues while still providing adequate friction. Before we move on, the final point I want to touch on is brake bias. Pad compounds can obviously be used to change the brake bias by varying the friction force generated at each axle. If the brake system bias was calculated and designed ideally, we'd generally start with using the same pad compound on the front and rear with matching friction characteristics which are suitable for our application. Assuming there's a dual master cylinder pedal box with bias bar, this will be the best method for adjusting the brake bias. In some extreme cases though, we might not be able to get enough adjustment out of the system, and it can be worth changing the pads since it's much simpler and cheaper than changing discs or calipers. and definitely a lot more practical than changing the master cylinder. Usually the case, especially with very front bias cars like front wheel drives, is that we can't get enough heat into the rear brakes, so we end up changing to a pad that'll work at a lower temperature, or sometimes to a more aggressive pad to generate more rear heat. Conversely, if the bias of the car is too rearward due to the disc or caliper sizing, then the fix could be changing to a lower friction pad in the rear. Either case quite likely results in the pad compounds having different friction characteristics as the temperature changes, and therefore the bias changes as the brakes heat up, which is clearly not ideal or consistent with our idea of good brakes. So while it's a feasible option to fix an imbalance, it's not the ideal solution. You'll be aware by now that choosing brake compounds is a detailed subject, and we've covered a lot in this module, so let's quickly recap the key points. The first step in choosing a brake compound is clearly defining the application to determine which characteristics we require. The big ones are generally noise and brake dust, operating temperature range, initial bite and brake feel, and of course the friction force they're capable of, keeping in mind that there's a fair amount of crossover and compromise with all of these. From here, we can look at the range of available compound options and the corresponding plots of the coefficient of friction versus operating temperature, and discuss with the manufacturer to determine what pads will work for us. After testing the brakes and using data or temperature paint, we can then understand any issues or room for improvement, checking if our pads are operating in the correct temperature range, and considering the brake bias to get the most braking performance out of our setup. This was just one of the many modules taken from our braking system design and optimization course. You'll start with the basics and build on the knowledge in this course to be able to design, tune, and optimize your braking system. If you're interested in advancing your skills, this is the course for you. For more information or to purchase this course, click the link to enroll now.